My dear students, after studying this module, you shall be able to define spectroscopy, learn basics of ultraviolet oblique visible spectroscopy, learn different kinds of transitions that can take place within the molecule, more so organic molecule which are important from forensic point of view, and you should be able to learn what are chromophores and auxochromes. Let us start with introduction. The spectroscopy is a branch of science that involves the study of the interaction of electromagnetic radiations with matter. Depending upon the nature of interaction between the electromagnetic radiations and the matter, several possible processes can take place that includes absorption. It occurs when energy from the radiative source is absorbed by the material. Now, extent of absorption is measured by measuring the fraction of energy transmitted through the material. Now, this absorption will decrease the transmitted portion. This is known as absorption spectroscopy. For example, UV-visible spectroscopy. Next is emission. It involves release of energy absorbed by the material. Emission can cause by absorption of energy by material from various sources of energy such as flames, electromagnetic radiation, as in the case of fluorescence. Now, third type is elastic scattering and reflection spectroscopy. This involves the reflection of or scattering the incident radiations by material. Fourth type is impedance spectroscopy. This involves the studies of the ability of a medium to show the transmittance of energy. For optical applications, this is characterized by the index of refraction. Next is inelastic scattering. This involves an exchange of energy between the radiation and the matter that shifts the wavelength of the scattered radiation. These include Raman spectroscopy and Compton scattering. Next type is coherent or resonance spectroscopy. These are techniques where the radiative energy couples two quantum states of the material in a coherent interaction that is sustained by the radiating field. The coherence can be disrupted by other interactions such as particle collision and energy transfer, and so often require high intensity of radiation to be sustained. Nuclear magnetic resonance (NMR) spectroscopy is widely used resonance method. Now, next is nature of the electromagnetic waves. As you all know, these are the waves that involve both electric and magnetic components, which give rise to their common class name electromagnetic radiation. In spectroscopy, only the effects associated with the electric field component of the electromagnetic waves are important. The whole electromagnetic spectrum is shown in figure 1. Ultraviolet and visible radiation comprise only a small part of the electromagnetic spectrum, which includes such other forms of radiation as radio, infrared, cosmic, X-rays. The range of UV radiation is 200 to 400 nanometer, while the range for visible region is 400 to 800 nanometer. Now next is origin of ultraviolet oblique visible spectra. Now ultraviolet oblique visible spectra arises due to absorption of electromagnetic radiation in UV oblique visible region of electromagnetic spectrum as shown in figure 1. The absorption of electromagnetic radiation in this region results in a transition between electronic energy levels in which electrons from the ground state of the molecule are excited to higher electronic state in molecule. The most probable transition is from the highest occupied molecular orbital HOMO to lowest unoccupied molecular orbital LUMO in a molecule as shown in figure 2. A UV visible spectrometer records the degree of absorption by sample as function of wavelength lambda of light absorbed, and the resulting plot between absorbance on y-axis and versus wavelength on x-axis is known as UV visible spectrum as shown in. Now the significant feature of UV visible spectra are lambda maximum, at which maximum absorption occurs, and the intensity of absorption. These parameters are characteristic of a particular molecule. Wavelength at which absorption occurs depends upon the energy difference between the ground state, that is HOMO, and the excited electronic state, that is LUMO. Larger the difference in energy between the ground and the excited state, lesser will be the value of absorption maximum, that is lambda max. UV oblique visible spectra generally consist of broad band of the absorption rather than single sharp line for each transition as shown in the spectra. The band-like structure of UV visible spectra arises as transition takes place over a wide range of wavelengths rather than a single wavelength. This can be explained on the basis that each electronic energy level in a molecule consists of closely separated vibrational and rotational energy levels, so that molecule can undergo electronic and vibrational rotational excitations at the same time. This results in a number of transitions that differ from each other only in a very small amount of energy, giving number of closely separated lines that the spectrophotometer cannot resolve. Thus, it gives a band-like structure enveloped over those closely separated lines. Now, types of transitions which are possible in organic molecules. In UV visible spectroscopy, molecule can undergo electronic transitions involving sigma, pi and non-bonding electrons. Among these, 4 types of transitions are possible depending upon the structure of the molecule. These include sigma star transition. This type of transition involves the excitation of electrons present in the sigma molecular orbital, which is excited to corresponding sigma star, that is anti-bonding molecular orbital, by absorption of electromagnetic radiation in the UV range. As you can see in the figure, the energy difference between sigma bonding orbital and sigma star bonding orbital is very large. So, these types of transitions require very high energy and thus absorb ultraviolet radiation of very short wavelength. These types of transition generally occur in alkanes such that methanes, because only sigma bonds are present, and the absorption maximum at 125 nanometer is due to sigma to sigma star transition. These transitions are of less importance because of their high energy. Now, next type of transitions are pi star transitions. This transition involves the excitation of electrons present in a pi bonding orbital to pi star anti-bonding molecular orbital. This transition requires a presence of unsaturated group in a molecule to take place and present in alkenes, carbonyl compounds, alkynes and azo compounds. Still another type of transition is N sigma star transition. This type of transition involves the excitation of electrons present in non-bonding molecular orbital N to sigma star anti-bonding orbital by absorption of electromagnetic radiations in the UV range. This type of transition requires a less energy as compared to sigma star transition, and thus it takes place at longer wavelength as shown in the figure. This transition is observed in saturated compounds containing atoms with unshared pair of electrons, such as saturated compounds containing oxygen, nitrogen, sulfur and halogens. Now, next type of transitions are N pi star transition. This type of transition involves the excitation of electron present in non-bonding molecular orbital N to pi star anti-bonding molecular orbital. This transition is of lowest energy, at the same time it is of low intensity as it is symmetry forbidden. As you know, the N orbital and pi orbital, they are not present in the same plane. For now, example of this is carbonyl compounds show this transition generally at 280 nanometer. Now, let us explain certain terms which we would be using in describing UV spectra. Now, first is chromophore. Chromophore is a part of molecule or group of atoms which is responsible for absorption of radiations. The nature of wavelength which is absorbed depends upon the nature of chromophore. The absorption of electromagnetic radiations results in the excitation of electrons from the ground state to excited state. From ground state to excited state, which depends upon how strongly these electrons are bound to nuclei, and hence depends upon the nature of group of molecules which is absorbing the radiations. The different chromophores are described below. The different chromophores are alkanes. Alkanes consist of only single bond and do not contain bonds with unsaturation or unshared pair of electrons. Thus, in this case, only transitions which are possible are sigma sigma star. These two energy levels have a large energy difference, due to which this transition takes place at high energy due to absorption of ultraviolet radiation of very short wavelength. Due to this, these transitions are of less importance and generally takes place at wavelength below 200 nanometer. Next chromophore is alkene. Alkene are unsaturated compounds that consist of double bonds in their molecules. Thus, they consist of pi electrons, which makes pi star transitions possible. These transitions are also of high energy and their position depends upon the nature of substituent attached. Still another type of chromophores are alkynes. Just like alkenes, alkynes also consists of pi electrons which make pi star transitions possible in them. Alkynes absorb near 175 nanometer in ultraviolet region. Next chromophore is carbonyl chromophore, which is present in carbonyl compounds. Now, carbonyl compounds consist of double bond between carbon and oxygen, so they consist of unsaturation, that is pi electrons as well as non-bonding pair of electrons present on oxygen. Thus, they can undergo pi star transitions and n pi star transitions. However, n pi star transition, as explained earlier, is symmetry forbidden and thus low intensity and takes place at 280 to 290 nanometer. The pi star transitions are allowed transitions and take place at 180 to 190 nanometer depending upon the structure of the molecule. Another type of chromophores are alcohols, ethers, amines and thiols. All these compounds consist of non-bonding pair of electrons, thus transition of the type n sigma star becomes important. This transition is of high energy and takes place at short wavelength. In alcohol, ethers and amines, this transition takes place in the range of 175 to 200 nanometer, while in thiols this transition takes place in the range of 200 to 220 nanometer. The characteristic absorption maximum for various chromophores is summarized. Absorption maximum for simple chromophores, alkanes, sigma sigma star transition 150 nanometer, alkenes pi pi star transition 175 nanometer, alkynes pi pi star transition 170 nanometer, alcohols, ethers, amines and sigma star transition 175 to 200 nanometer, sulfur compounds and sigma star transitions 200 to 220 nanometers, carbonyl compounds pi pi star transition at 188 nanometer and n pi star transition, which are symmetry forbidden transitions, occur at 280 to 290 nanometer. The presence of some groups with chromophores in a molecule may change the absorption characteristics of chromophores. Such substituents groups increase the intensity of absorption and possibly changes the wavelength of absorption and known as auxochrome. The typical example of auxochrome are methyl, hydroxyl, amine and halogens, etc. The effect of these substituents can be further divided into following categories: red shift or bathochromic shift. The presence of auxochrome may result in a shift of absorption maximum towards longer wavelength or lower energy, which is called bathochromic or red shift. Bathochromic shift may also observe due to change in solvent polarity that will result in solvatochromism. Next, auxochrome may result in blue shift or hypsochromic shift. The presence of auxochrome may result in a shift of absorption maximum towards shorter wavelength, which is called hypsochromic or blue shift. Now, auxochrome can result in hyperchromic effect, an increase in absorption intensity due to presence of substituents with chromophore is called hyperchromic effect. Auxochrome may also result in hypochromic effect, a decrease in absorption intensity due to presence of substituent with chromophore is called hypochromic effect. We can very well explain by taking this figure into account. Now, next is what is the effect of solvent on visible or UV spectroscopy. The solvent is used for dissolving a compound under investigation and has a large effect on UV/visible spectra of a compound. The fine structure of absorption bands is first blurred due to interaction of the solvent and the solute molecules. This effect is more pronounced in case of polar solvents as compared to non-polar solvents. The fine structures of UV/visible spectra is best observed in vapor phase. The solvent polarity also affects the position of intensity of absorption maximum. However, this shift depends upon the nature of the compound, that is, whether the compound is a polar compound or a non-polar compound. The change in solvent polarity does not cause any significant shift in the absorption spectra of non-polar molecules, as in the case solvent-solute interactions are minimum. The absorption spectra of non-polar compound is practically same in polar solvent such as alcohol as well as in non-polar solvent such as hexane. In the case of polar compounds, the absorption maximum is generally affected by solvent polarity. The effect depends upon the type of transition taking place within the molecule. Now, coming to n-pi star transition, with increase in the solvent polarity, blue shift is observed. This shift towards shorter wavelength is mainly due to greater stabilization of more polar ground state than the excited state through dipole-dipole interactions. Formation of hydrogen bonds or solvation with the polar solvent, as a result of which energy difference between the ground and the excited state is increased and absorption shift towards shorter wavelength. In case of pi-pi star transitions, with increase in solvent polarity, bathochromic shift is observed. As in this case, excited state, which is more polar, is stabilized with increase in the solvent polarity, which thereby decreases the energy difference between ground and the excited state, resulting in bathochromic shift. The n sigma star transitions are very sensitive to hydrogen bonding with solvents. For example, alcohols and amines form hydrogen bonding with solvent molecules due to the presence of non-bonding electrons on the heteroatom. As a result of this, ground state gets more stabilized as compared to the excited state, resulting in blue shift in the absorption maximum. Now, let us discuss the effect of conjugation on UV-visible absorbance. The presence of conjugation in a molecule always results in a bathochromic shift. The larger the extent of conjugation, more will be the bathochromic shift. The presence of conjugation not only increases the absorption wavelength, but it also results in increase in intensity of absorption. The electronic energy levels come close to each other in the presence of conjugation, that results in the transition of lower energy or of longer wavelength, as is explained in figure 6. For example, ethylene absorbs at 175 nanometer, while 1,3-butadiene absorbs at 217 nanometer with 2 double bonds, whereas 1,3,5-hexadiene absorbs at 258 nanometer because of the presence of 3 conjugated double bonds. Now, the beta carotene, figure 7, which is responsible for the red color in carrots, consists of 11 conjugated double bonds, which absorbs in a visible range at 265 nanometer, thus appears red in color. Now, summarizing what all we have studied till now is, we have studied UV-visible spectra arise due to promotion of electrons from the ground state to excited state. due to absorption of electromagnetic radiations in UV visible region. The promotion of electrons takes place from sigma to sigma star or pi to pi star or n to pi star or n to sigma star, depending upon the nature of the molecules in terms of its structure. Transition from sigma to sigma star requires high energy and takes place at a shorter wavelength, while transition from n to pi star requires a least energy, hence takes place at longer wavelength. The part of the molecule or atom which is responsible for absorption in UV region is called chromophore. The group attached to chromophore can change the absorption characteristic of chromophore is called auxochrome. The absorption maximum also depends upon the choice of the solvent and depends upon the nature of the compound. Both hypsochromic or bathochromic shifts may be observed with change in solvent polarity. The presence of conjugation always results in decrease in energy levels between the two electronic energy levels, thus gave bathochromic shifts. Larger conjugation, more will be the bathochromic shift.